Hi everyone, my name is Rob Chatterjee. I'm a PhD candidate with the University of Queensland's Sustainable Minerals Institute. Today I want to talk a little bit about my PhD research entitled Learning a Mineralized Fault Network from 3D Seismic. I'm supervised by Professors Rick Valenta, Jack McLaughlin, and Dion Weatherly at the university. I'll start by outlining my research problem. And that is to address a declining discovery rate of minerals deposits. The next generation of mineral resources will require novel subsurface exploration technologies, harnessing new data formats in order to sustain our industry. 3D seismic is one such dataset that is gaining acceptance for its utility in reducing not only exploration, but mining risk at depth. And that's important because a lot of the new deposits will be discovered deep underground. The current methods of employing 3D seismic used in minerals exploration have some serious limitations that I hope to address. I think I'm addressing a bottleneck in limiting the rollout of 3D seismic's adoption through the minerals industry, and that's manual seismic interpretation. In manual seismic interpretation, we're trying to map faults in the 3D dataset. And I think it has three costs associated with it. And those are capital, labor, and error. Error, I think, is most significant because whenever you involve a human in a decision-making process, they bring with them their own set of psychological biases, and they're more prone to make mistakes than automated algorithms. Currently, there are no techniques to automatically interpret 3D seismic datasets for minerals exploration. And there is no way to assign a quantitative measure of uncertainty to interpreted structures. So I'll outline my research objectives following that, and they are three. First, we're trying to develop an automated method for fault surface extraction from 3D seismic datasets that can be used in minerals exploration. Second, we're trying to create an exploration tool to identify exploration markers for mineralization. And those can be quartz faults, clay alteration, depending on the deposit we're targeting. Third, we want to provide uncertainty on predictions in order to rank drill targets. We have a finite drilling budget. We want to allocate drill holes to the places where we're more confident in there being a structure present. So my research plan is divided into three phases. And I've completed the first phase, and that's to do with developing synthetic data to train a machine learning fault prediction algorithm. I'm extending a method developed by Wu et al. At the University of Texas in Austin that uses synthetic data to train a machine learning algorithm that can map faults for the purpose of petroleum targeting. The key difference with my research is that the geological complexity of a typical hard rock terrain that hosts a mineral deposit is a lot more complex than a sedimentary terrain that would host petroleum resource. As such, I need to introduce more geological complexity in terms of folding and faulting into the synthetic data. And that's what I've done. And I'll run you through that in a little while. In phase 2 of my research and in phase 3, I'll be using a machine learning algorithm that is trained on these synthetic custom data to map fault structures in 3D datasets from a operating gold mine in Queensland. In phase 2, we'll be extending Wu's model, a 3D convolutional neural network, and it can make binary predictions. So if you divide up the fault, the seismic cube into small blocks, each of those blocks will have an associated prediction, either being a fault or not a fault. But we hope to do a little bit better than that in the third phase by introducing multi-class predictions. And we want to introduce other forms of data besides the seismic data. That could be the drilling database, for instance, to allow us to make predictions on faults, non-faults, silica faults, or clay alteration, for instance. Importantly, we also want to introduce uncertainty in order to provide some information to exploration decision making, so they can rank drill holes according to their geological prospectivity and their confidence in structures existing underground. So in the first phase of my research, I applied the Wu machine learning algorithm to map faults at the operating gold mine dataset that I'm working with. We found that it highlighted some large fault structures, and we wondered whether this was a result of the training data that was fed into it. And it was. We found that the training data is comprised of these large volume spanning faults. And so it's no surprise, I suppose, that in the real data set that the fault that is extracted of a similar dimension to the training data faults. So in a hard rock terrain, the important faults are much smaller with respect to the size of the seismic volume. So we need to make those faults a lot smaller, but we also need to increase the complexity in terms of geological folding and geological faulting. So we adapted the Wu method to introduce more folds, more pronounced folds, and we also introduced more faults. We can accommodate way more than the 5 to 6 faults that the Wu team incorporated in their training data. And our faults are modeled on a well-accepted method of modeling fault displacement fields in 3D that essentially mimic the laws of physics. Furthermore, our faults are multifractal, and that is a pattern that we see in nature where a fractal is a repeating pattern at different scales. So length of faults and the slip on those faults are both fractal. Because slip is a function of length, both being fractal, they become multifractal patterns. And so we model that in our data. Here's an example strike slip fault using the Okada model for 3D displacement fields. And here is a dip slip fault using the same model. So we can create physically realistic fault deformation fields. And when we introduce folding, we get a training data set that looks like this. And here we've got one fault represented by these covered glyphs. But as I mentioned, we can introduce many more faults. And so this is an example data set, training data set that has more than one fault. In fact, 5 faults. But we can incorporate that. So now we've created synthetic images, we need to create labels. We do this by creating volumes that have voxels associated with a fault or non-fault. We numerically assign a value, a grayscale value, so that we can create these volumes that show the ground truth, if you like, of fault locations in the synthetic data set. It allows the algorithm to learn the true location of the faults. And as you can see, our faults are a lot smaller versus what the Wu team created. And we performed some validation to make sure that the labels matched up with the 3D deformation fields. And so now we can generate as many of these data sets as we like, and we can modify their complexity to suit the target we're trying to extract data from in the field. And so hopefully in a year's time, I'll have some more information, some more research results surrounding the machine learning section of my research. And I look forward to presenting to you then. Thanks very much for listening. If you have any questions, please direct them to the contact details here.